In this video, what we're going to do is we're going to calculate inverses. In our previous video, we identified inverses. Now we're going to learn how to, when given one function, how do we find its inverse? And so we're going to start with this given function. It says, determine whether each equation defines a one-to-one function, then find the inverse. I'm not going to super go into depth about what a one-to-one function is. There's other videos out there for that. But let's just jump into finding the inverse. So our way that we calculate the inverse is I'm going to write my function in terms of y and x. And then what I do is I'm going to interchange x and y. And then I'm going to solve for the new y. So I'm going to solve for that y, so I'm going to subtract 5 from each side. Then I'm going to divide by 2 on each side. And normally I'd be good with just leaving it as this, but since we're going to graph it, I'm going to rewrite this over here in slope-intercept form. So I'm going to write it as x over 2 minus 5 over 2, which can simplify even further. X over 2 is the same thing as 1/2 x, so we have a slope of 1/2, and that minus 5 over 2 is the same thing as minus 2.5. So I'm going to kind of copy this up here, and our notation that we use for this inverse function is, it looks like a little -1 exponent. And so we have our original, we have our inverse. Now, let's kind of talk about this one-to-one stuff real briefly. What we have here is if I graph my original, it's got a y-intercept of 5 and a slope of 2. So just a rough sketch would look like that. And that would be my f of x function. And the reason that this one-to-one, what this means is that every element in f of x's domain corresponds to one element of its range, and vice versa. Meaning, if this graph were to curve back down so that we had 2 points that had the same y value, if it did that, it's not one-to-one, okay? Or, if it were to curve back this way so that I had 2 points that had the same x value, then it's not one-to-one. So, and maybe in layman's terms, you can think of it as like, as long as the graph doesn't like double back on itself and curve back either sideways or up and down, it will be one-to-one. And so, this is a one-to-one function. Therefore, this inverse, or what we calculated, should be a good inverse for it. And one way we know graphically if it's an inverse is we're going to graph it and see if it's reflected over y equals x. And here's what I mean by that. If I graph that, we've got a y-intercept of -2.5. And we have a slope of 1/2, so I'm going to rise 1 and run 2, rise 1 and run 2. And our graph for our inverse, and I'll label it, is going to look like that. We know this is a good inverse because remember, one of our ways of knowing or identifying inverses is those inverses should be a reflection over the line y equals x, which I've kind of shown here in purple. It appears that our inverse function is a reflection of the original over this line. So what we've calculated is a good inverse. Let's do our second one. It says, determine if it's one-to-one, then find the inverse. Well, let's calculate the inverse first, and then we'll graph it, and then we'll worry about the one-to-one stuff after that. So what I'm going to do is I'm going to interchange x and y. And now I'm going to solve for my new y right here. So my first step is I'm going to take the cube root of each side of my equation, because I want to undo that third power exponent. And I'm left with y minus 2 equals the cube root of x. My last step is I'm going to add 2 to each side of the equation to isolate the y. So that means my inverse function, if I use that inverse function notation, f inverse of x equals the cube root of x plus 2. Now, let's kind of graph both of these and then we can answer the one-to-one question. If I'm looking at this original graph, and I'll graph it in blue, it looks like it's the cubic function shifted to the right 2 units. So if you're good at graphing your parent functions, I'm going to shift to the right 2 units, and I'm going to graph that cubic function. So if it's okay if you don't just know how to graph this off the top of your head, but you can always graph it using a calculator or something, but I think it's helpful to know how to graph that. It's going to look something like that, not a perfect graph, but something kind of like that. And that's our original function, f of x. And as you can see, this is a one-to-one function. This works. This graph never doubles back on it. It never turns back to the left, or it never turns up over here. Every element in its domain. In other words, every x has only one y, and every y has only one x. So this is a one-to-one function. Therefore, this should be a good inverse. Let's go ahead and graph this. This looks like the cube root function shifted up 2 units. So if I shift up 2 units, and I graph the cube root function, which looks kind of like this. Once again, not a perfect graph. I'm just trying to get a rough sketch of it so we get the idea. And I'll label this. This is our f inverse of x. We know this is a good inverse, or the graph confirms that this is a good inverse because it's a reflection over the line y equals x. Okay? We should be able to reflect this red function over this like it's a mirror, and it should land on the blue function. If it does, then we have a good inverse. Let's look at a third example. Determine whether each equation defines a one-to-one function, then find the inverse. Well, let's do our same method. Let's calculate the inverse first, and then we'll have a little discussion looking at the graphs. So I'm going to interchange x and y, and I'm going to solve for my new y. I'm going to take the square root of each side. And this is what our inverse should be. It should be that f inverse of x equals the root of x minus 2. So if I'm going to graph my original in blue, it looks like the quadratic parent function shifted up 2 units. And then my inverse function is the square root function shifted to the right 2 units. And you can see that these aren't exactly inverses. Okay? If I were to draw my line of reflection y equals x, it doesn't look exactly the same over here as it did up here. What supposedly is our inverse function does not really match the original function. And the reason that is our original function isn't one-to-one. Remember how we talked about that one-to-one? Look right here. Okay? I can grab these 2 points, and they are 2 points that have different x values, but they have the same y value. This means this is not one-to-one. So for now, not one-to-one. Okay? Therefore, currently, this is not the inverse. So if it says identify if it's one-to-one first, you might just want to do that first and then stop there. Okay, we're learning in later videos about restricting the domain of this. But for now, I would just say these are not inverses because this is not a one-to-one function.